The contribution of Francis Galton to statistics cannot be overestimated. He indicated that statistics provides summaries of information concerning large groups. In this conception, he claims that collection of large data in large numbers is essential for scientific research. And then statistics exploits the smooth continuity in which objects of the same species vary. In this conception, first, he put statistics at the service of understanding evolution, understanding heredity. And he indicates that, for example, if you measure the height of plants or height of humans, and you put large numbers of units of analysis, one after the other, and you order by, in this case, the height of these units of analysis, then you have a smooth continuity. So there are no big jumps between the height of one unit of analysis and the following. It's continuous and smooth, the difference in height, provided that those objects or those units are members of the same species. If you find a not smooth, that there is no smooth continuity, when you put objects in order, then that probably means that those objects belong to different species. And then he provided a genetic explanation of this smooth continuity. He says that the distribution of a trait is caused by a combination of large number of small influences. This conception is profound and is advanced to his time. He first gives a causal explanation. And that's something that we're going to see what happened to that original idea of Galton. But the second one is a problem that current genetic research is finding. If you try to find the genes of intelligence, genes of depression, genes for schizophrenia, all these are traits that by behavioral genetic studies, like studies using the twin method, we know that there must be some innate influences on those traits. So when we start now being able to collect data on genes, then we expect that we will find the genes for those traits. But what scientists are finding at the moment is that there is no one gene for intelligence, there is no one gene for schizophrenia. There are multiple genes which vary, that they have variations or alleles, and these variations provide a very tiny, minute difference. Now, by the combination of all these by the combination of all these small influences, if some people have the, so to speak, beneficial alleles in those genes, then they will be better than others. But because there are a lot of genes that are involved in one trait, then the differences will be small and smooth. Now, he provided a tool to try to explain his conception of statistics and genetics. it's called the quincunx, or later known as the Galton board. And you can go to YouTube, to this link and many other links, to see videos in which they explain how this works. Now, the idea is simple. You start with putting a pebble here, and then the pebble goes down. And then these pegs, they bounce in these pegs, and then there is a 50% chance that they will go one way, and 50% chance they will go the other way. And again with the following peg, and again, and again, and again, and again. So, at the beginning, when you put the pebble on the quincunx, you've no idea where it will finish. It will finish somewhere there. But if you put a lot of them, then a pattern emerges. And the pattern is a pattern that we can see here. We can see that the pebbles concentrate more in the center than on the sides. This, in fact, is called the binomial distribution, but it's an approximation of what we call the normal distribution. Now, why do we call this quincunx? Okay, that comes from the formation of dots in a die. When you have a 5 in a die is represented by this pattern of dots, this pattern of 5 dots. And quincunx, it comes from a Latin way of saying 5. So that's why it's called the quincunx. Now, there was a problem with this observation, and this problem you're not going to see in the multiple YouTube videos that explain how the Galton board works. The problem is that it's not good to give a hereditary explanation of the phenomenon. In the second version of the quincunx, Galton tried to simulate the existence of 2 generations. So the first one would be A and the second one would be B. He added this central segment that wasn't there before and divided the game into 2 parts. First, the pebbles go down and they stayed in A. If that happens, well, the distribution of the pebbles will be normal, or approximating normal with the binomial. Now, let's say now we've got the pebbles with that distribution of in A, and we remove the floor where the pebbles are sitting, and the pebbles start coming down and they end up in B. What happens is that the distribution will also approximate a normal distribution, but there will be more pebbles on the sides than before. It will be something like this. And if you continue with C and D and E, you will find that the distribution will be wider and wider and wider and wider. And Galton saw a problem with this. On the one hand, it could explain variability, how variability occurs in evolution. But that's not what he observed with his measurements. He measured height on plants that come from 2 generations, and he did that with humans. So, parents and offspring. And what he found is that the distribution remains the same. So, he then provided a third version of the quincunx, and it was this one. So he had to add these shoots in order to restrict the possibility of the pebbles to expand and have a wider distribution to the one that they started with.